I don't ever slow up, no I don't take sh**. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up. I don't ever slow up, no I don't take sh**. I got no love for the fakeness. If you want.
Okay, let's start with our topic today. Our topic is AC, which stands for alternating. That is perfect. Alternate. Anyways, we're not going to write AC, né? We're not going to write alternating because I don't know what spelling that is. I don't know who's writing that. Anyways, okay, so let's start with our topic AC. Now, AC current, that is the one that ESCOM is supplying us with. Are we together, right? We get our current from ESCOM as AC. Now, let's make a distinction between AC and DC. And let us try to see the difference between AC and DC. That is going to make it easier for us to understand AC once we understand DC. Are we together, right? Now, let's start from the sources. Where exactly do we normally get our DC current? Normally we get it from batteries, right? We get it from solar panels. We get our DC from even DC generators. Now, with a battery, let's say for an example, you've got a 5-volt battery. You know 100% that the current coming from there will always be 5 volts. It will never be less than 5 volts. It will never be more than 5 volts. It is a constant source of power. Are we together? And the voltage is always constant. Are we together, right? And if we are going to put that on our graph, right? Our graph will have a value that is like this. So if this is your 5 volts, you'll have your 5 volts going all the way up like this. This is our voltage, this is time, whatever, right? Unless your battery starts to die down, that's where you see your current sliding down like this. But on normal cases, your 5 volts is just constant. Are we together? Now let's move on as well. How many wires do you have in DC? Mostly 2 of them, right? A positive and a negative. Now, that simply means that one of the wire is hooked up to the positive part of the battery and one of the wire is hooked up to the negative part of the battery. Are we together, right? Now, that means your current can now complete a full circuit by your battery here. Let me just draw a nice battery. This is positive, this is negative, and then this is our light bulb. So, this will always be negative because it's connected to the negative, and this will always be positive because it's connected to the positive. Are we together? There is no change in the wires that now the positive has decided, there was a mistake, I was supposed to be negative, but I'm positive. That never happens. Are we together? Okay, let's move over to AC. Now, AC, from the name AC, it means it is alternating, right? It never has one value. Are we together? Even if I'm to ask you this question right now, right? The answer that you're going to tell me is wrong, no matter what you guys say. Here's the question. What value of voltage do you get from ESCOM? What is the standard supply of voltage? 210. Is it telling the truth? We talked about it on Monday. 230, that is correct, right? We get 230, maybe 225, maybe 235 sometimes, right? But mostly it's like a constant 230 volts. But what if I'm to tell you that no matter what you say, that value is wrong, right? Because it's alternating. That means your values will never be the same. Are we together? Your values will always fluctuate from 0 to 220. They can even go as high as 310 volts. Are we together, right? Yes, that's the current you're getting from ESCOM. Now, let me ask you guys a question, right? With AC power, right? We've got 2 wires. Are we together, right? Now, on our 2 wires, we've got the live and we've got the neutral. Are we together, right? Now, the live is responsible for being the one that carries power. That's what you've been told all along, right? The live brings power. But what if I'm to tell you, yes, but not really? Would you guys believe me? Yes. Okay. Now, if you have to look on DC, right? On DC, you've got one specific, like let's say for example, here we're dealing with electron flow, right? Let's just say it's electron flow. So we say our current goes from negative to positive, right? But now here, there is no, our current flows from live to neutral. Are we together? There is no such thing as that. Your wire can bring electrons, or your wire can bring current, and your neutral can take it back or your neutral can also bring current and the live can take it back. Are we together? Now, remember the example that I told you? Class of 2012, Serima High School, right? If you still remember, hopefully, I really wish that some of the guys that I go to school with, they watch my YouTube channel. I really want that to be the case, you know what I mean? Okay, so remember the example that I told you about the door frame, that we used to charge our phones in the door frame, right? That we used to hook up to any wire. It didn't really matter whether the wire was brown or the wire was blue. As long as it's not earth, we'll just hook up a wire to that live or to that neutral. And then the other wire will wrap it onto a metal door frame. Are we together? Then we'll charge our phones there. That proved to me that there was no live and there was no neutral. Are we together? Both of these wires are responsible for bringing electricity and they're responsible for taking it back. Are we together, right? There is no electron flow, there is no conventional current flow in AC. All of these two wires can do the same thing simultaneously. Are we together, right? Now, let's move on to how exactly does that work, right? Where exactly does our current come from? Now, if you have anything that produces AC, let me ask guys a question, right? What normally produces AC? Generators. That is correct, right? So our AC generators, they are circular in shape. Are we together, right? Our AC generators, all of them are circular in shape. Are we together? And then inside the generator, the way that the generator is made is that there are poles inside it. Now, these poles, they have got a magnet. Are we together, right? These poles, the job of these poles is to produce a magnetic flux. So you'll have a north pole and a south pole inside your generator in all cases. Now, because of that, you will have a magnetic flux that goes from north pole to south pole. Or you'll have a magnetic field that goes from north pole to south pole. Are we together, right? Now, here's the thing. You see, remember there is a law, right? Which says that wherever you've got an interaction between the magnetic flux and the conductor, right, you will have current induced onto the conductor. Are we together? Remember, this is my mistake. I told you about it. Was it on Monday? And I'm not willing to correct it. I'm willing to die on that mistake. Okay. So the thing is, whenever you have got a current carrying, whenever you've got an interaction between the magnetic flux and the conductor, right, current is induced into that conductor. So let's just look at it in this way. Now you've got Faraday's second law, right, which says that the amount of EMF, right, that is induced onto your conductor is dependent on, number one, right, the angle at which your conductor interacts with the magnetic flux. Are we together? So here I didn't tell you this the last time, did I? I just like to say it's a circular generator, blah, blah, blah. Well, sometimes I give you necessary lies. Hope you guys will forgive me. Okay, but now since we'll be on YouTube, it will be fact-checked by millions of people. So, well, I'll be very lucky if I get millions of people checking this. But anyways, okay, now you have got your magnetic flux, the north pole and the south pole, and your magnetic flux is like this. Now, if I remember generators, we talked about generators last time, right? The ones that make noise outside, right? We said they've got about three main components. You've got a tank, you've got an engine, and you've got a generator, right? The tank provides the fuel. The fuel then is converted to mechanical energy, right? And then the mechanical energy is the one that moves the generator, right? Now, inside the generator, what it is actually moving is a bunch of conductors that are rolled up. Let me check to see if I've got my armature here. Yes. Okay, this is an armature of a DC generator, right? But in our case, if it's an AC generator, it wouldn't have this. This is a commutator. An AC generator does not have a commutator. So this is what is rotated, right? Now, if you are to check, if you are to look at it even in this way, right? You will see that these are wires. Are we together? Conductors. Are we together, right? So because of that, the generator, the engine moves the generator. Now, let's look at our conductor. Let's say this pen is a conductor, right? Now, wherever there is interaction between the magnetic flux and the conductor, current is induced onto that conductor. So, at the beginning, there is no current induced into it, right? Because it's flat. It's parallel to the lines of force. So if we were to plot that on our graph, here is the voltage, and then here is the time, or you can say this is the angle, whichever one you want to say, right? It's completely okay. Now, as soon as your generator starts, as soon as your engine starts moving, it moves the conductors inside it, right? Now, here's the beginning. When it starts to move, it cuts maybe 1 or 2, 3 lines of force. And because of that, you will have a little bit of current induced. Are we together, right? And then, as soon as your conductor starts moving, it cuts more and more and more lines of force. The more lines of force it cuts, the more EMF is induced. Are we together? Now, the maximum amount of EMF is induced onto your conductor when it is at 90 degrees, right? So it feels like this at 0 degrees, and then this is our 90-degree angle. And at 90 degrees, you can now see that it is perpendicular to the lines of force. That means your conductor is cutting all the magnetic lines of force. Are we together? So at 90 degrees, this is where you've got your maximum current induced. So this is your 90 degrees. And then after that, your conductor starts cutting less and less lines of force. Are we together? As it goes down to 0. Now, when it cuts less and less lines of force, that means the power induced is less and less, up until we get to that 0 point. Are we together? So it started like this, and it did a 180, now it's turning the other way. Now, in terms of AC, it does not have a commutator here, right? The job of the commutator is to reverse the current. Are we together? Now, let me give you an example. You can see our magnetic flux still flows from North Pole to South Pole. Are we together, right? They haven't changed directions at all. Still North Pole to South Pole. But if we are going to look at our conductor, started like this. So if we can say if it started like this, current was being induced in this direction from the butt of the pen to the cap of the pen, right? And if it does a full 360, now check what's aligning with the magnetic flux now. The current is now induced from the cap to the butt. Are we together? That means it has reversed the direction inside the wire itself. Are we together, right? So if it was traveling like this at the beginning, then a full 180, then it's now traveling like this. Are we together? But inside your cap, if it changes directions, we call that a negative value. Are we together? So our current now does the exact same thing, but on the negative side. Are we together? This is known as your sine wave. Now remember what I asked you, right? You say there is no constant value in AC, right? Yes, that was correct. So let me rub this part out, and then we draw the sine wave. So let's redraw our sine wave, right? Our sine wave now looks like this. Now, the highest part of your sine wave is called the maximum. Are we together? Or you can call it your peak. Why do you call it the peak? Because it's the highest point, right? The peak of the mountain, the highest point. The toppest point of your mountain, of the mountain. Now, let's go back to our graph, right? Now, let's look at this. There is no constant value of current, right? If you say, okay, our AC value is 230 volts, right? And I'll tell you where, at what point, right, do we have a constant 230 volts here, right? There is no point in the graph where we get a constant 230 volts. Are we together? But we have got what we refer to as our RMS. RMS stands for root. That is correct. Root mean square. Are we together? And the root mean square is the equivalent AC, right? Let me drink water and study English. So my English gets finished sometimes, I'm sorry. Okay, let's start again. Root mean square, right? Root mean square is the equivalent DC value of an AC power source. Are we together, right? Let me repeat that part again. Because on AC, we don't have a constant value, right? But if we look at everything that uses AC, has got a constant output. Are we together, right? If you look at the lights, a constant brightness. If you plug in your TV, right, your TV doesn't switch on and off. It's a constant picture that comes out. Are we together? Anything that uses, there is a charger there, right? Your phone doesn't charge like this unless maybe it's an Apple. But you know, Samsung phones don't charge like that. So everything that uses AC has got a constant output. Now, RMS, it is a property of an AC waveform that is responsible for the constant output properties. Are we together, right? Perfect, perfect. So wherever you hear people saying that, no, our AC value is 230 volts, 235 volts, what they mean the root mean square. Are we together? The root mean square, that's your 230 volts. Let's move over to this part here. This part here is T, which stands for your period. Are we together? The period is how much time does it take to finish one cycle. Are we together? Now, what is the normal period for the current in South Africa? Yes. Go on. You missed another zero. That is correct. 0.02 seconds. Now, next we've got something that is referred to as frequency. Now, frequency is the number of the number of cycles that your waveform completes in 1 second. That's what frequency stands for. Are we together? What is the standard frequency of South Africa? He knows it. What? No, we're not in America, Mineros. That is correct. That is absolutely correct. 50 hertz. Let's move on, right? Let's look at how components react to components. Oh man, thank God they don't mark English. React to AC. Or let's see how AC affects our electrical components, or how our electrical components affect our AC values. Are we together? So let's start with number one. Let's start with the resistor. Resistor. What's the job of this one is yours. What's the job of a resistor, Mineros? To resist. You don't sound sure, but you are correct, right? The job of the resistor is to resist current or to limit current. Are we together, right? Now, a resistor, because it's like a solid state thing, right? There is no extra thingy happening there, right? It's just, straightforward. So with a resistor, it does not change any properties of your waveform. Are we together? It just limits the amount of current, but the waveform that came in is the exact waveform that is going to come out. Are we together, right? Exactly, right? So, and resistor does not change anything, right? So in other words, you can say does not affect the waveform, right? So if it does not affect the waveform, let's look at this graph here that I've just drawn, right? Now, this is our 0 point here. And then this is whether it is going to affect it for the better or for the worse. Are we together? Now, because a resistor does not affect anything on our AC waveform, everything that has to do with resistance is always on the x-axis. Are we together? Because nothing has changed. So since the resistance doesn't change anything, the change is going to be 0. Are we together, right? Since current that flows through a resistor before and after the resistor does not get changed, so the change is also 0. Are we together? The voltage that flows through a resistor before the resistor and after the resistor still remains the same, right? No property of that voltage is changed. So the change is also going to be 0. That's why everything to do with a resistor is always on your x-axis. Are we together? Next component, which one should we start with? Capacitor or inductor? You guys are a fan of capacitors. Capacitors, sweet. Okay, let's talk about a capacitor, right? Now, before we actually understand what is a capacitor and how a capacitor affects, this whole thing that we have here, right? What we're going to do is we're going to look at the construction of a capacitor, and we're going to look at how a capacitor works. So, if we explain what is a capacitor and how a capacitor works, then now we can now start to say, oh, that's why. You get me, right? Okay, so let's start. A capacitor is made like this. You have got one conductive plate. Are we together? I've got a capacitor here. Let me show you. So I tried unsuccessfully, right, to open this capacitor. Now, if you're to, I tried unsuccessfully, trust me. Now, if you're to open this capacitor up, right, you find out that there are plates, sheets. Yeah, let's just call it sheets, right? There are sheets like this, but then these sheets are rolled around in circles. Are we together like this? To make this cylindrical thing that you see here. And each sheet has got a terminal that is connected onto the output. Are we together? Now, in between these sheets, we have got an insulator. So this is sheet number 1, which is represented by this terminal here. It's connected to the first sheet. The second terminal is connected to the second sheet. Metal sheets, right? It depends on the capacity. Some of them can be metal, but as long as it's very, very conductive. And then in between, you've got an insulator. Now, this insulator is known as a... That is correct. Dielectric. Are we together? So you've got your 2 capacitor plates. These are very, very conductive. And then in the middle, you've got a dielectric. So if you have to open this capacitor up, you find out that these plates, these capacitor plates are rolled around in a circle so that you can just have more square area, right? The more area you have, the more places where a lot of electrons can be stored. Are we together? Because the job of a capacitor is to store electrons. It's like a battery, but a horrible battery, right? Horrible. Anyways, let's move on, right? So remember with AC, right? Our current comes and goes. Are we together? That means our current comes in this direction and it also comes in this direction. Are we together, right? Okay, so before we move on, let's just explain a capacitor as if it's working with DC, right? So what happens with the capacitor is when your current is flowing. Here's my first question of the day. Menzi, this one is yours. What is current?
Current.
That's why I told you guys to take a break. Yes. No, you're correct.
Is the flow of electrons.
Flow of electrons. Orbit killed you. That's why I told you guys to take a break. I said I don't want zombies in my class. Orbit made you into zombies. Anyways, you are correct, right? Electrons is the... Oh, sorry, you say current is the...
Flow of electrons.
Flow of electrons. It's together, right? So, that means our electrons are flowing, right? Let's just say this is DC current. That means they are flowing in one specific direction, right? They are coming from A, they're going to B. There is no dancing around, there's no stopping in the middle, right? So when your electrons are flowing through, they are going to pass through the capacitor plates, right? Now, as soon as they try to cross over to the next plate, there is a dielectric in between. And we said a dielectric is an insulator, which then blocks and says, nah, you're not going where you want to go, right? Blocked. So our electrons now are just going to accumulate on the capacitor plates, right? So remember, we've got a voltage. Voltage is making...
Is a force.
Force. Minerals.
I wasn't going to say that.
Okay, so voltage is a force. Are we together, right? So the voltage is forcing the current to move, right? The voltage is forcing the electrons to move in one direction. And there is nowhere for these electrons to go. So they are just going to accumulate. And remember, I told you that if I find a good example, I'm never going to let it go, right? So my favorite example is that example of the balloon. And I'm never going to let it go. So, for an example, you take a balloon and then with a hose pipe. Now, you open the tap on the other side. The pressure from the tap is your force because it's forcing water in one direction, right? And then the water is your current because the electrons are the ones that are moving. So that is represented by the water. And then you've got a balloon here, right? Now, the water is going to accumulate inside your balloon. Are we together? That is a perfect example of of how a capacitor works. The current accumulates on this end of the balloon, and the water cannot go onto the other side because otherwise the balloon will have to burst, right? Now what happens if your capacitor is rated for 12 volts, but you put 230 volts? What happens to your capacitor? Kaboom, right? Same as your balloon. If you are to open it too much, then your balloon is going to blow up. Are we together? So your balloon expands by holding water in. Now, that's how your capacitor charges. How would you get it? And how your capacitor discharges is if this voltage then is to be equal to 0. How would you get it, right? So let's say, for an example, you've got your balloon full of water, then you close the tap, and then you remove it from the tap. What's going to happen? All the water that is in the balloon is going to? Exactly. So that means all these trapped electrons that are here, they are going to flow back out together. And your electrons, they flow back in the opposite direction. Out together. That's exactly how a capacitor works. So that's capacitor charging this, capacitor discharging. Out together. Now, let's look at our waveform, right? Then let's see how exactly, let me draw another waveform. Let me draw a big one this time. This is not big. But you know, they said it's not the size that matters. Anyways, let's move on. Let's move on, right? So here's the thing that's going, right? This is what's happening. This is your positive side, and this is your negative side. That means at your positive side, the live wire is bringing in current. And on the negative side, the live wire is returning the current back. Are we together? So this will be positive, this will be negative. So this is what is represented by this graph. Are we together, right? So if you have it here on the positive side, so I want you to think of it in this way. On the positive side, your current is coming through. Are we together? But then it's going to be blocked and it's just going to accumulate here, right? And then as soon as we get to this 0 point and we get to the negative side, right? It's like your balloon has just been opened up and all the water is going to escape backwards. Are we together? And because of that, the maximum, the examples that I have in my head, God forgive me. Anyways, let's move on, right? As soon as we are here now at 0, right? All the water that is in the balloon, because it has got so much force trapped inside it, it is going to be why are you laughing with the force? Now, all the pressure that has been built up, right, is going to be released. So the maximum amount of current, remember, because current is the flow of electrons, right? So the maximum amount of current is released as soon as we get to 0. Are we together? And after that, then the rest can trickle its way out back to 0. Are we together? Yes. So it goes to maximum, right? Yes. And then after it goes to maximum, then the remaining is like this. I don't have a balloon, but let's say I had a balloon, right? Let me give you an example of a balloon. Let's say we've got a balloon full of air right now, right? And then we just left it. What's going to happen?
The air will come out.
Right? There's so much force that actually makes the balloon fly. But then as soon as time goes on, the force reduces and your balloon will end up falling on the ground, right? That's exactly what happens here. A maximum amount of current is here at the beginning, and then as you go on and on and on, the amount reduces and reduces and reduces up until you get to 0. Then the process repeats again this side. Are we together? The process is always going to repeat and repeat and repeat and repeat. So as you can see, we said we are supposed to get our maximums here at the top. Are we together, right? Now if we're going to cut this into degrees, our maximum, we said we get it at 90, then here we've got 0, here we've got 0, here we've got 0, and then our other maximum, we also get it at negative 90. Are we together? So here we got our maximum at 180. Are we together? We are supposed to get our maximum here at at 270, but you got our maximum at 180. So because of that, our current has been released early. Are we together? I know releasing early is not a good thing, but our so in this case, our current has been released early. So because of that, you can now say current through the capacitor is leading by 90 degrees. Are we together? That's where the 90 degrees leading is coming from. Are we together? So you said your capacitor leads by, current through the capacitor leads by 90 degrees. Are we together? But according to Ohm's law, according to Ohm's law, right? Resistance is equals to voltage divided by current, right? We're looking at that formula, right? Resistance is equals to voltage divided by current. Okay, so let's just talk about this formula in a little bit. This means that our resistance is directly proportional to our voltage. That means that these two are directly proportional, right? They go together. But then it is inversely proportional to current. That means if your current increases, what happens to the resistance? Decreases. Are we together? So, and what happens to your increase in resistance? What happens to the voltage? It also increases. That is correct. So here we are going to, since we now know the relationship between current and voltage, current and resistance, we know that these two, they don't go together at all. If current increases, the voltage is going to decrease. Are we together? So because of that, our voltage through the capacitor always lags. Are we together? So you're going to say the voltage through the capacitor lags by 90 degrees. Are we together? Oh, this is lagging by 90 degrees from zero. If you look at it like this looks like 180, right? It's lagging by 90 degrees from zero. This one is leading by 90 degrees from... Nice. Okay, now, let's talk about the next thing, right? If we have to look at this capacity here, there is no form of resistance, right? I remember we are electrical engineers. The resistance of a conductor is always negligible. Are we together? Or zero. So, because of that, we have zero resistance. Are we together? But, oh, there's always a big but. But, right? Okay, here's the thing, right? But there is a voltage drop that happens here. Are we together, right? Now, the voltage drop is caused by the fact that we have got AC that is flowing through here, right? That means current comes in this direction, and then as soon as we get to zero, it's repelled in the opposite direction, right? Current comes in this direction on the negative side, right? And then it is repelled as soon as you get to the positive side. Now, because of that, there are always inefficiencies in every system. Are we together, right? Those inefficiencies are what causes voltage drops, right? Because of this movement back and forth, back and forth, back and forth, we're going to lose some of our power. That is what is causing the voltage drop. Now, that voltage drop, we now call it our reactance. I said L, sorry. We now call it our reactance. Are we together? Reactance is X. So, what is causing the voltage drop? It is reactance, right? That means that our capacitor is reacting to this. So, because of that, that is what becomes our equivalent resistance. Are we together, right? It is not resistance, but it is the equivalent resistance. Are we together, right? Like, let's have an example. I am thirsty. We're having coffee in the morning. You guys love coffee, right? I had coffee this morning. Here's the thing. You're having coffee in the morning. And then you realize that you run out of milk. Then you use cremona, right? Is cremona milk? No. It is made from soya beans, right? Yeah, it's not made from milk. I used to think that they would dry milk and then no, it's made from soya beans, right? So it is not milk, but it is acting like milk when you put it into your coffee in the morning. So in this case, your reactance is not resistance, right? But it is acting like resistance. It has got the same function as resistance. Are we together? And it is calculated by the formula 1 over 2 multiplied by pi multiplied by f. Now, f represents for frequency. Are we together? Because the faster you spin it, right? No, John, I wasn't saying that to my hands. I was saying...
Please continue, sir.
So, here's the thing, right? Frequency is how many times does this thing go per second, right? So, the faster your waveform moves now, right? I'm not doing this anymore, right? The faster your waveform moves, right? That means that your reactance here, right, is going to reduce, right? So, just imagine, picture this, moving slowly or moving fast. If you're moving slowly, you're going to get more tired along the way, right? You're going to lose a lot of things along the way. Think of it like this way. You're taking a trip to Zimbabwe. You're using a bus and you're using a plane. If you're using a plane, you'll be there in 1 hour 45 minutes, right? That means you don't even need to eat anything. But if you are taking a bus, 16 hours at best, right? And in those 16 hours, you're gonna buy KFC there, your KFC. So you're losing more money along the way, right? So that's exactly what happens. The faster you spin or the faster your frequency moves, then the less your reactance. Or in other words, the less your resistance. If we're quotes, resistance, then multiply by the capacitance itself. Are we together? So your capacitance also goes here. Since, oh sorry, so this is supposed to be a C. Since we say that resistance is directly proportional to your voltage, so these two go together. Are we together? Okay, let's look at the last part. Let's look at inductor. Are we together? I'm going to wrap this part up. Let's see how exactly does an inductor function. An inductor is the last part, right? Inductor. Now, let's look at exactly what exactly is an inductor before we talk about how does an inductor function, right? So, an inductor is a wire, just a wire, right? And then we, I see you doing this. So I'm just going to do this. That's a beautiful inductor, by the way. This is a beautiful drawing, actually. I can promise you guys will never draw better than this. You guys don't know. Okay, so this is our inductor. Are we together, right? An inductor comes in many different shapes, different sizes, and in different forms. You can find a cyclical inductor. I don't have one, but it will be like this with a with the iron core, and then the wires are coiled around it. Or you can even find it like this and the wire coiled around it. Are we together? But the basic function or the basic construction of a conductor is just a wire that is coiled around a ferromagnetic material, which means it's a material that is able to, take full advantage of the magnetic flux. Are we together, right? Okay, so we know that any current carrying conductor has got a magnetic field around it, right? Now, what if you coil that current carrying conductor? You then concentrate. Let me give you an example, right? You take a very long wire, you coil it up, you can fit a long wire into a very small space because you've coiled it up, right? Then it doesn't take a lot of space. So, if you take a long wire, you coil it up into a very small space, that means you then concentrate a magnetic field on a very small space. That's how you make your magnetic field stronger. Are we together? 3 factors that influence, I need you to know these 3 factors by your heart. So number 1, we say the number of, it's coming back. It's
number of turns.
Number of turns, that is correct. Number 1, number of turns. And then number 2, I'm going to skip the best for last, right? Number 2, who said type of material? You did. Type of material. I want you to say type of core. The thing that you put in the middle, right? The type of core, that is correct. And then the last one, the best for last, is the amount of current, right? Because any current carrying conductor produces a magnetic flux. So the amount of magnetic flux that is produced by that current carrying conductor depends on how much. Exactly, that is correct. So here we've got our magnetic flux that is produced by our current. Are we together, right? But our current is coming from AC. Are we together, right? Now, what this means is, let me wrap this part off. Here is my new waveform. Now, what this means is that, right, if the magnetic flux is directly proportional to current, right, or if the current properties are the same as the properties of your magnetic flux, that means your magnetic flux is supposed to follow what the current does. Are we together? Since the current is producing the magnetic flux, that means if there is no current, there is no magnetic flux. If you've got a maximum current, that means you're also supposed to get maximum magnetic flux. So these two are directly related. Are we together, right? Okay, so let's move on. So if your current, right, which is here, increases, that means your magnetic flux increases. If your current reduces, that means your magnetic flux reduces. Are we together? If your current then changes directions, then it's now flowing in the negative direction. That means your magnetic flux is also supposed to negative direction. That is correct, right? But, oh man, there's always yes, a big word, right? So here's the but, right? Here's the but. There is also a law that says whenever you have an interaction between the magnetic flux and a conductor, current is then, I keep on saying current, let me correct myself, an EMF is then induced onto the conductor. Are we together? Right? So here's what's happening now. Your current increases, right? So does your magnetic flux, right? Your current reduces, so does your magnetic flux. And your current collapses. Before I even got to this, do you guys still remember? I'm sorry, guys. Do you guys still remember Lenz's law? Let's explain Lenz's law for us, right? Lenz's law states that, I'm going to explain it because I keep on forgetting the words. But here's what Lenz's law says. Lenz's law says that if you have got a magnetic flux, right, that is inducing an EMF into a conductor, right? We do know that any current carrying conductor has got a magnetic flux around it. So that means this magnetic flux induced a current. But because the current is now there, this current is also going to produce its own magnetic flux. And the magnetic flux that is now produced by this current opposes the original magnetic flux. Does it make sense?
Yeah, we are getting there, but
now, let's re-say Lenz's law again. But then this time, let's focus on voltage, right? Now, we've got a law that says any current, remember you can't have current without voltage, right? Because you can't have something moving without something that makes it move. So any current carrying conductor has got a magnetic flux, right? But then this magnetic flux is produced by AC. That means that this magnetic flux is also going to collapse onto the conductor. And when the magnetic flux collapses to the conductor is going to have an EMF induced into it. And then that EMF induced then opposes the original one. Actually, the EMF is called back EMF. Are we together? Because it always opposes the original one. So if the original EMF is going in this direction, the back EMF goes in the opposite direction. Are we together, right? Okay, so let's move over to this format, this AC circuit now, right? So our current increases, so does the magnetic flux. Our current collapses, right? Our current reduces back to zero, and your magnetic flux collapses. And the magnetic flux collapses on itself. Are we together? That means that the magnetic flux interacts with the conductor. Are we together? And when it interacts with the conductor, you're going to have an EMF produced. And the EMF goes back. Are we together? But we are already at zero here, right? Which direction is, remember that this is the EMF, right? This is the EMF that produces the magnetic flux, right? And when it produces the EMF, the back EMF, which back is it going to go? It can't go to this side because it's still the same side, right? It goes back onto the negative direction, right? So that means you are going to have a maximum amount of EMF that is induced onto your conductor before the maximum EMF is actually produced. Are we together? Does it make sense? So that means that because of the back EMF, which is not like just 1 volt or 2 volts, that's the maximum amount. Are we together, right? So that means we're getting the maximum amount before we are supposed to get the maximum amount. Are we together? And if we are going to look, this is 90 degrees, this is 90 degrees, right? That means that we are getting our maximum EMF 90 degrees before we're supposed to get it. Are we together? That is the reason why the voltage through the inductor is always leading. Are we together? And obviously the current will then lag. Are we together? So you're going to have your IL down here, right? The current is lagging.
before we go There, are you trying to say that we're having two magnetic flux on one conductor?
No, I'm saying we are going to have two voltages on.
One conductor.
Exactly. But then it's not going to be two voltages, because by the time the second voltage is produced, right, the other voltage that was there is already now at 0. So we've got a voltage here, right? And then this voltage collapses. And when this voltage collapses, then you're going to have that back EMF that is then produced, the maximum amount of it. And then, but by the time the waveform actually gets to produce its own voltage, we already have the voltage that is going in the same direction. So it looks like your voltage is just going to decrease slowly as we get back to 0. So because of that, our voltage leads and our current lags. Are we together? Oh, by the way, this is the most important diagram ever. This is known as your phasor diagram. Are we together? I want you to memorize the phasor diagram. Through hell, till death do you part. Are we together? The phasor diagram. You must never forget it. Okay, but this is a conductor, right? These are just wires. There is no resistance there, right? But because of the magnetic flux interfering with the current flow, we are going to have a little bit of resistance. But then this resistance is not due to the resistance. It is due to the magnetic flux. Are we together? That means that the inductor is reacting with the current. And what do we call it? Reactance. Are we together? That's why we've got an X. And X is your reactance. And XL. The L is the symbol for your inductor. Are we together? So XL is equals to 2 pi FL. F stands for frequency and L stands for your inductance. Are we together? So here's the thing. Remember, back EMF is only produced when it collapses, right? And your frequency is how many times a second, right? So if your frequency increases, the amount of times it collapses increases. Are we together? That means that your magnetic flux is now interfering too much with the current that is flowing through, right? And because of that, the equivalent resistance of your inductor increases. Are we together? So here you can say that XL is directly proportional to your frequency. Are we together? So here you're going to have your XL up there on top. Are we together? Your phasor diagram is now complete. Are we together? Okay, so let's see what happens, right? Let's try to calculate the total resistance of a circuit that has got a capacitor, an inductor, and a resistor. Are we together, right? Now, if you look at this, right, the resistance is going in its own direction, the capacitive reactance is in its own direction, and the inductive reactance is in its own direction. Are we together, right? Now, because all these three are going in their own direction, how would we add them? They're going in their own directions, right? How can we possibly add things that are going in separate directions, right? So, we're going to use Pythagoras theorem. Are we together, right? Let me just take that part out and let me redraw it like this. It's like this, right? This one is going up, this one is going down, this one is going sideways. Are we together? So if we're going to add the two up, it's almost like we are looking for a resultant between these two things. Are we together, right? So according to Pythagoras theorem, r squared is equals to x squared plus y squared. Are we together? X being the x-axis, y being the y-axis, r being your radius that goes either like this or like that. Are we together? Or in this case, you can say r is your resultant. Are we together? If you're going to do the mathematics, you can say, okay, I only want to look at r. You remove the square, you put the square root, you're now left with something along these lines. Are we together, right? Now, let's take this mathematical formula, right? Let's apply it here. So that means Z, which is our impedance, right? Our impedance is our equivalent total resistance. That is correct. Equivalent total resistance. Now, our formula is going to go like this. What is on our x-axis? It is our resistance. Are we together? So it's going to be resistance squared plus what is on our y-axis? It's XL and XC. Are we together? but they are going in separate directions. If things are going in separate directions, what do? Do we add them or subtract them? That is correct. We subtract them. That means this is what I prefer you do. Although whatever you do really doesn't matter, right? But I always prefer so that you can have this inside your heads at all times, right? Is to start with whichever one is on top. So I'll prefer XL minus XC close bracket squared. Let me make this clear. Although it doesn't really matter which one you start with. Even if you start with XC or start with XL, you're going to get the same answer. Are we together? Even if your answer here becomes negative, negative squared will always give you a positive. Are we together? Yeah, this is only applicable in series. Are we together? Because you can only add resistors together in series. Are we together, right? Perfect. In parallel, impedance is calculated using Ohm's law. Are we together? Which says V over I. This is how we add it in parallel. Parallel. Okay, let's move over to current, right? If you've got a series circuit, what happens to the total current in series? It remains the same. So if your current remains the same in series, that would then mean the only way we can now calculate our total current is to use Ohm's law. Are we together, right? So here it will be total voltage divided by your impedance. Are we together? Let's do the last part. Also, if it is now a parallel circuit, how do you add three currents that are going in different ways? We do the same thing. Are we together? Pythagoras theorem. So here we're going to have our IR squared. Are we together, right? Because we are adding, but we're adding things that are going in different directions. And then it's going to be IC minus IL, close bracket squared. I always want us to start with the one on top. I just want us to have it in our heads that you always start with the one on top. So this one is for series. This one is for parallel. Yeah, that's what I'm spelling. Parallel. Perfect. Then let's look at the voltage. The voltage is the last part, right? What happens to the voltage in series? Voltage in series, it? Are you sure? You looked at me like, are you serious? Yes, you are correct. The voltage in series, it adds up, right? So we're going to add the three voltages the same way again. That means we're going to have VR squared plus open bracket VL minus VC close bracket squared. Are we together? And what happens to the voltage in parallel? Series, this is parallel. What happens to the voltage in parallel? Adds up or stays the same? Stays the same. So that means we now have to calculate it using Pythagoras theorem. Are we together? We should then IT multiplied by Z. Are we together? Right? That's how we do our calculations. Now, let's move on, right? So, since IT in series, ZT, so since Z in series, IT in parallel, and VT in series, right? We are looking for the resultant. Are we together? So our resultant can either go in this direction or it can either go in that direction. Are we together? That leaves us with an angle here that we can calculate. Are we together? This angle is what is known as your phase angle. Are we together? If you're in N4, N5, and N6, you can then use this phase angle to calculate your power factor. Are we together? Even N2, N3, they can ask you the power factor. Power factor, just write this down for me. Power factor is equals to cos theta. Just write it down for me. They are going to ask you that. Because in mathematics, wow, this is like 3 subjects in one. Industrial, maths, and science. I should be getting paid triple for teaching you things in 3 subjects. Okay, so let's move on, right? Okay, so here we've got our right angle triangle, and then here we've got our angle here, right? If we're going to go to maths, what do we call this side here? It's our opposite. Are we together, right? And what do we call this angle here? This side here? It's our? That is correct, right? And here this side is our height. That is correct. Now, if you are looking for this angle here, what do you guys use? SOHCAHTOA or In high school, we used Chasho.
We use soccer toys.
Chasho tour, I think.
No, it's soccer toys.
Soccer tour. Oh man, you guys keep on forgetting I'm old. I was in high school 1997. You guys are not even born yet. Well, your parents are not even born by then. Okay, so let's move on, right? So let's use soccer tour, right? I don't want you guys to have tons of formulas. And I feel like a lot of formulas are just going to confuse you and crowd your brains. I'd rather have you guys have only 2 formulas, right? But if you want, you can make 3 formulas, as long as you know where the formulas are coming from. I don't mind you guys forgetting formulas, as long as you know where the formulas are coming from. So you can forget all these, right? As long as you remember where the formulas are coming from, then you can make up the formulas on your own. Are we together? Even if the question is to come out slightly different. Like let's have an example. Your question comes without an inductor, right? You can do it on your own because you know your phasor diagram. You just remove XL, VL, and IL. Then you're done. Then the whole thing remains same. Even here on the formulas, you just have to remove this. Are we together? So I don't mind you guys forgetting the formulas. I want you to know where the formulas came from so that you can make up your own formulas. Are we together? Okay, so car. Then let's start with tan, right? So car. We're starting with cos, right? So theta says cos theta is equals to adjacent over hypotenuse. That is correct, right? So yes. And our adjacent is this one on our x-axis, right? Now, if we go onto our phasor diagram, what is on our x-axis? It's our resistance. So here that means it's going to be resistance divided by, and what is on our hypotenuse? Hypotenuse is our resultant, right? And our resultant is Z, which is your impedance. That is correct. But what if, for an example, the question, this is R by the way. What if you now it looks like something else now. It's R. Okay, so let's move on, right? What if you are not dealing with resistances? What if you're dealing with currents, right? Still the same thing. It will be cos, and then instead of R here, it will then be I R divided by I T. Are we together? If you're dealing with voltages, it will be cos, and then here it will be V R divided by V T. Are we together? Same formula. I just want you to remember one of them. And then you know that when you're dealing with different things, you can use any of them. Are we together, right? Then let's move over to the last one, which is tan, right? How do you pronounce it? Tan. 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 And tan is equals to SOHCAHTOA. It's opposite over adjacent. That is correct. Now, this side is our opposite, right? And what's on our opposite side here? You've got IC, you've got IL, you've got VL, you've got VC, you've got XL, you've got XC. That means that on our y-axis, it's only for the capacitor and the inductor. Are we together? So let's start with this one. So it will be tan X. Now, you see where I always told you, always start with the one on top, right? So I'll prefer XL minus XC divided by R. Are we together, right? Depending if the question did not give you an XC. Like let's say for example, there's no capacitor in your question, it will just be XL divided by R. Are we together, right? Or if you're dealing with currents, it will be tan, or don't forget -1. It's arctan, right? Arctan, arc So here it will also be equals to IL minus, or here I'll prefer IC minus IL, close bracket, IR. Same as this side as well. Tan arc, it will now be VL minus VC, close bracket, VR. Are we together? These are our formulas. This is an explanation of AC. The only thing left under AC is resonance. Are we together? But I think we've explained everything. And I'm not sure if you have resonance in N2 anyways. But I would want us to do resonance tomorrow and we can explain what is resonance in detail. Are we together?